Look at a standard topographical map, and you are faced with a dense, chaotic web of intersecting lines. These maps are excellent for pinpointing the exact elevation of a specific spot, but for communicating the average steepness of an entire region, the data is often lost in the visual noise. In 1930, C.K. Wentworth introduced a systematic mathematical solution to this problem. His method translates complex contour density into a clean, readable average slope map with distinct, smooth gradient zones. Creating one requires a 1 to 50,000 scale map, tracing paper, a ruler, and a pencil. You also need a scientific calculator capable of calculating the inverse tangent. Converting raw elevation into regional slope values allows geographers to categorize the landscape by its physical behavior, identifying where high gradients drive intense erosion. Start by overlaying a sheet of transparent tracing paper onto your delineated drainage basin. Draw a uniform grid over the basin, ensuring each square is exactly 2 by 2 centimeters. On a 1 to 50,000 scale map, this 2 by 2 centimeter square represents exactly 1 square kilometer in the real world. Label columns with letters and rows with numbers for a coordinate system. Next, isolate grid square B2 to extract our core metric, the contour crossing. Tally every instance where a contour line intersects the boundaries of B2. Here, we count 56 crossings. Log that total crossing count for square B2 in your worksheet. Divide that total by 4 to calculate the average number of crossings per kilometer. For square B2, our average is 14. This average crossing number serves as the raw mathematical proxy for surface roughness within that specific square kilometer. Now we use Wentworth's formula to convert that raw count into a degree of slope. First, multiply your average crossings by the contour interval used on your map. Using our average of 14 and a 20-meter interval gives the numerator. For the denominator, use the constant 636.6, required for metric grids to ensure accuracy. Using your calculator's inverse tangent function for square B2 yields a slope of 24 degrees. Log this final degree value into your worksheet for square B2. This simple operation has transformed abstract lines into a specific, comparable value for regional steepness. Now transfer that calculated value back onto your tracing paper. Place the degree value in the absolute center of its corresponding grid square. With the grid populated, we draw isopleths, lines that connect points of equal value. Sketch smooth, curving lines between these plotted center points to clearly separate zones of gentle terrain from steep hillsides. These lines represent geomorphological behavior, showing exactly where gravity has the most influence over the landscape. Compare your original topographic map with your new average slope map. Look at the spatial pattern to see where the highest slope values are clustered. High-value clusters often indicate the upper basin, where steep gradients result in intense river downcutting and erosion. In contrast, the lower values show you exactly where the terrain flattens out as it approaches base level. Wentworth's method allows you to look past the individual lines of a map and identify